Hi, I'm Professor David Farina. In today's video, we're going to be talking about life in the universe, life in the solar system, and the galaxy. Let's get started. So, as we were talking about in previous videos, life as we know it is carbon-based. And it appears that here on Earth, at least, life originates in the water, underneath the oceans. So, where else do we see in the solar system that has these criteria? Where else do we have water that's in any state? Or, more importantly, in its liquid state? Our best bet so far is Mars. Mars appears to have liquid water in a form of briny underground water that appears to make its way to the surface on a regular basis. Some other possibilities out there are Europa, which is a moon of Jupiter, and Titan, which is a moon of Saturn. There are some other places, but most of them are all ruled out. So what about some alternative biochemistries? Maybe life could be based on silicon rather than carbon. Or maybe instead of water, the substance ammonia or methane could be a potential way that life could flourish. In fact, we know of methanogenic life forms that live right here on Earth. So it's not a stretch to say that these could be something that would exist throughout the solar system. So, what is life? As we've discussed in previous videos, it's complex. So the Drake equation is a way to try to understand how life could be calculated. How could we determine how much life is out there? So all of the stars of the Milky Way would be in this big green box here. Now, within that box, let's assume that we have star systems that have the following criteria. Let's assume we have a small fraction which have planets. Now, to be clear, it's thought that at least half and probably all stars have planets. But let's assume for now that we have a small percentage of these stars that have planets. Within those, how many of them have habitats? Habitats would be an area that would be suitable for life. Within that, how many of them have life? Within that, how many of them have intelligence? Within that, how many of them have culture? And then this last box, enduring technological societies, are represented by the smallest of boxes here. So how could we calculate this? So the Drake equation does its best to try to do this through a number of steps. The first step is we have to understand what the Drake equation is trying to do. It says the number of technological intelligent civilizations now present in the galaxy. That's what we want to know. How many of those are out there? So Drake said, here's what we're going to do. We're going to take the rate of star formation averaged over the lifetime of the galaxy. We're going to multiply that by a fraction. By comparison here, this is going to reduce that number. So we've got how many stars do we have multiplied by a decimal number here, a fraction. So how many stars have planets? Multiply that once again by a fraction, average number of habitable planets within those planetary systems. Once again, we multiply that again by the fraction of those planets now that are in the habitable zone, where it's not too hot, it's not too cold, the temperatures are just right. How many of those habitable planets are going to include life at all, where life evolves, multiplying that by, once again, a fraction of how many of those are now intelligent life that are able to develop technology, and then average lifetime of a technologically competent civilization, which here on Earth, technologically competent civilization may last for a really long time, or depending on how our society treats the planet, and how we treat each other in regards to things like war, and how disease treats us, it's a question mark. We don't know how long human civilization is going to last. Hopefully a very long time, but this is an unknown. So when we calculate this all out, it's dramatic. You can get various different answers, and it's all up for debate. So I'm going to give you a quick scenario. If I start off with 100 million stars, okay, and let's assume, just to make this easy, that each of these is 1%. So I have 0.01 is my multiplication factor, or 1%. So I have 100 billion stars. If I said 100 million, I apologize. 100 billion stars multiplied by 0.1, or 0.01. We get, out of 100 billion, we still get 1 billion left, okay? 1 out of the 100 billion. So we have 1 billion stars. I multiply that again by 0.01, or 1%, and I find out that of my billion stars now, if I multiply by 0.01, I get 10 million total planets with habitable zones. Now, I multiply that again by 1%, and I end up with 100,000 habitable planets within our galaxy that life arises on. I multiply that again by 1%, and I get 1,000 planets where life-bearing planets, where intelligent life evolves. Oh, that's a huge number. Okay? 1,000 with intelligent life right within our galaxy. I do this multiplication again, and I get 10 that intelligent life develops a technological society. That could be us. There could still be 10 out there. Now, we don't know what the average lifetime of a technologically competent civilization is. So, based on this, we could say, right now, it's possible there's other life out there. And this is a very low number, by the way. We think that the fraction of stars having planetary systems is not 1%, but probably all planets. At least 50%. So right there, we multiply this number by, instead of 0.01, we multiply it by 1. And we still have the same number of stars left, which makes a big difference in our numbers later on. So the Drake equation is always up for debate. People talk about this all the time. Some people have a modified Drake equation where they add things to the Drake equation to make it even harder for life to exist. And the reality is it's very complicated, and we really don't have an answer. But as soon as we start to find any signs of life out there, I think that this is going to be a very important equation that we start to look at more closely. And I, as a scientist and as a person, really think that the Drake equation is good, but if used in the wrong way, it can make it seem like life is going to be very, very low in numbers, or from a different perspective, somebody could make it seem like life is extremely abundant in the universe. So just be careful when you find information about the Drake equation, to take it with a grain of salt. The rate of star formation, 10 stars per year, divided by the population of the Milky Way by its present age. Okay, this is a different way of doing it than I just did. The fraction of stars having planetary systems like our own. And every time we do this, we find that the number of planets are going to be probably pretty high that have potential life. So another factor here is that our sun is a one solar mass star. If our sun were bigger or smaller, that's going to play a role in what kind of habitable zone we have, and the distance from that star that a planet would have to exist at in order to be in that habitable zone. If the star is bigger, then the planets need to be farther away. If the planet is very small, if the star is very small, then the planets are going to have to be very close in order for them to be in the habitable zone. And so those are some considerations scientists must make. Star densities around the galactic bulge are very, very high. The sun lives around this area of our galaxy, where the galaxy's habitable zone might be. So this is some other considerations we might want to make, is that maybe star formation is too high and star deaths are too high, and maybe that makes it challenging for life to take hold. Maybe it makes it easier. We're not sure. The potential for stars in binary systems to have planets. Well, we do know that we've detected planets around binary star systems, but how does this affect life? We're not sure. We're still finding out about these worlds, and we need to learn more. And there are various different ways they can orbit, as you can see here. So, as we look at all of these experiments, it's suggesting once again that it might be very, very easy to make life in the universe. Or, depending on the numbers we plug in, it might be very, very hard to make life. We're not sure. So, once again, there's no facts here. Just speculation, just opinion. And you'll find this throughout the internet, throughout the scientific world, is that when it comes up with life in the universe, people's opinions get used more than they probably should. We don't have any data to really point at, to use, and as a result, it's a very difficult and challenging discussion to have, and I think it's important, once again, to come in with an open mind. Now, an interesting concept here, the fraction of planets where intelligent life develops and uses technology. So where are we on the grand scheme of things? We've got radar technology, which is what has been historically used by the SETI Institute, the Search for Extraterrestrial Intelligence, where we're looking for life in the universe, which we'll talk about in a little bit. So, is the technology of radio the one that we're going to be using forever? That's likely not to be the case. As we develop, we're going to see new ways that life might be able to be detected in our universe, and one of those is now laser technology. So lasers might prove to be a way to detect life out there. The goal here is we need to keep our eyes open. So as we keep moving forward, once again, we have a lot to think about. We have to determine, what is life? How is life going to evolve in other places, around other stars, on other worlds? And unless we keep our eyes open, unless we keep our options available, we're going to have a difficult time finding life in the universe. But I think if we look hard enough, at some day, we might find it. Thanks for watching. I hope you liked this video. If you did, please click the like button. If you would like to learn more, please subscribe. And if you'd like to get a notification each time I make a video, please click the bell at the bottom. Thanks again, and have a great rest of your day.